In this video, we're going to learn about two more important examples of families of groups, which are the additive groups of integers modulo a number n, and the multiplicative group of integers modulo a prime. Before we do that, I've copied on this slide the full group table for the dihedral group D6 at the top there, so you can compare that with your answers. Anyway, let's begin with the definition of a congruence class. So we're going to take an integer a and a positive integer n. Then we define the congruence class of a modulo n, which we write like this, in the following way. The congruence class of a modulo n is equal to the set of all integers, which you can get by adding a multiple of n to a. So this captures actually some familiar concepts, because if you look at the congruence class of 0 modulo 2, that will be all the things of the form 2k for k in z. In other words, it's the set of all even integers. But actually that's also the same as the congruence class of 2 modulo 2. Because if you think what this is by definition, well, it's the set of all things of the form 2 plus 2k for k in z. But we could simply rewrite this as the set of all things of the form 2k plus 1 for k in z. And that makes it clear that these are actually the same set. And similarly, the congruence class of minus 2 or 4 or minus 4 modulo 2, those things would all be equal to the set of all even integers. On the other hand, if you look at the congruence class of 1 modulo 2, that congruence class consists of all the things of the form 1 plus 2k for k, an integer. So that is precisely the set of all odd integers. And again, if you look at the congruence class of 3 mod 2 or minus 57 mod 2 or any odd number mod 2, then what you'll get is the set of all odd integers. So there are only two different congruence classes modulo 2. There is the set of even integers and the set of odd integers. And if we move on to looking at congruence classes modulo 3, well, if you look at the congruence class of 1 modulo 3, what you'll get is all integers which leave remainder 1 when you divide by 3, because the definition of that congruence class is set of all things of the form 1 plus 3k, where k is an integer. So that is the set of all things which leave remainder 1 when you divide by 3. It's all things of the form 1 plus a multiple of 3. Again, if you look at the class of minus 2 or the class of 4 or the class of anything which itself has a remainder 1 on division by 3, then its congruence class modulo 3 will just be the same set, the set of all integers with the remainder 1 on division by 3. And similarly, if you look at the class of 0 mod 3, that's all the multiples of 3. And if you look at the class of, say, 2 mod 3 or 5 mod 3 or minus 1 mod 3, that's the set of all integers with the remainder 2 on division by 3. So this is the definition of a congruence class modulo a number n, and those are the things which are going to make up the elements of our additive group modulo n. Before we get to defining that, we have to define a relation called congruence modulo n. So if we have two integers x and y, we say x and y are congruent modulo n if and only if their difference is a multiple of n. So their difference, x minus y, is divisible by n. And the notation we use to say that two integers are congruent modulo n is this. There's a connection between congruence modulo n and these congruence classes modulo n, as the name suggests, which is that x is congruent to y modulo n if and only if the class of x is equal to the congruence class of y mod n. So let's try and prove this result. So let's suppose that x is congruent to y modulo n. That means they differ by a multiple of n. Their difference is divisible by n. So let's say x is equal to y plus k n for some integer k. Actually, let's use a different notation, because we use the word k when we define classes. So let's say a n, some a in z. Now I have to prove that the two congruence classes, class of x and the class of y modulo n, are equal. So let's take an element in the class of x. So we know what it looks like. It looks like x plus kn. So let's take this to be an element of the class of x. So k here is an integer. So x plus kn is equal to y plus a plus kn. Right, just substituting for x and collecting together the terms which are multiples of n. And now this thing is y plus an integer multiple of n, so that's an element of the class of y. Okay, so we've now proved that every element of the class of x is also an element of the class of y. But very similarly, you can show that every element of y of the class of y is also an element of the class of x. So if y plus kn is an element of the class of y, then y plus kn, this arbitrary element of the class of y, again we can rewrite it using the fact that x is y plus an, so y is x minus an, so that's x plus k minus a times n, that is x plus an integer multiple of n, so it's in the class of x. So we've shown that the two classes are equal. We showed that every element of the class of x was an element of the class of y, and every element of the class of y was an element of the class of x. So we've proved that if x and y are congruent modulo n, then their congruent classes are equal. So conversely, we have to suppose that their two congruent classes are equal and prove that x and y are congruent mod n. But lucky for us, this is even easier, because if the class of x modulo n equals the class of y, then, well, x is an element of the congruence class of x because it's x plus 0 times n. So it's an element of the congruence class of y. So x is equal to y plus a multiple of n for some integer k. Alright, but now x minus y is equal to an integer multiple of n, and therefore, by definition, x is congruent to y mod n. Okay, so these two notions are completely connected to one another. Two integers are congruent modulo n if and only if their congruent classes are equal mod n. And that proves some of the observations that we made on the other slide. Like we said, the class of 1 modulo 2 was equal to the class of 3 modulo 2. And we now know that this is true without actually having to work out what those two congruent classes were, because we can tell for sure that 1 minus 3 is equal to a multiple of 2. So the result that those two congruence classes are equal follows from the fact that 1 is congruent to 3 mod 2. Okay. Although there are many different labels for congruence classes, because you can think about the class of 1 mod n and the class of 2 mod n and the class of 3 mod n and the class of anything you like mod n, there are not many different congruence classes. In fact, as the lemma says, every congruence class modulo n is equal to one of the class of 0, or the class of 1, or the class of 2, up to the class of n minus 1. Let's see why this is. So the key observation is that you can do division by remainder. So n is some positive integer, so you can divide a by n to get a is equal to a multiple of n, so q is called the quotient, plus a remainder r. And the key property is that you can ensure that the remainder is always a positive number or a non-negative number which is less than n. But if you look at what this equation here tells you, well, it tells you that a minus r is equal to a multiple of n. So a is congruent to r mod n. Since a and r are congruent modulo n, it must be, from the lemma on the previous slide, that the two congruence classes are equal. So that means the congruence class of any integer a is equal to the congruence class of its remainder when you divide by n, and its remainder is one of these numbers, 0 or 1 or 2 up to n minus 1. So that proves that every congruence class is equal to one of those things. But could a congruence class be equal to two of them? In other words, could two of the congruence classes on that list be equal? So we're trying to get this exactly part of the lemma. So how can we show this? We need to show that if you have two numbers, so I and j, which are greater than or equal to 0 and less than n, and if the class of I is equal to the class of j, then actually I must be equal to j. So let's think why this is true. So if the class of I equals the class of j, well then if we look at the class of j minus I, that's the same as the class of 0. So the reason for that is that if the class of I is equal to the class of j, then by the lemma on the previous slide, I minus j, I is congruent to j mod n. So I minus j is a multiple of n. And if that's a multiple of n, then I minus j is congruent to 0 modulo n. So the class of I minus j, or j minus I should have said, not that it makes any difference, is the same as the class of 0. That means because j minus I is a multiple of n, and j minus I is between 0 and n, because j and I were both greater than or equal to 0 and less than n, actually j minus I must be 0, because the only multiple of n which fits into this range is 0 times n. That means j is equal to I. Okay, so we've established that the thing which we're going to call z subscript n, which is the set of all congruence classes, modulo n, this is a set of size n. So this is the notation we use for the set of congruence classes. We use the symbol for the integers, this bold Z with the subscript n, to mean the set of congruence classes mod n. And while it looks like there are infinitely many classes, actually what we've proved is that there are exactly n different congruence classes modulo n. We're now going to turn that set Zn into a group under an operation which we will write with a plus symbol. And the way we define this plus symbol is like this. We define the class of A plus the class of B to be equal to the class of A plus B. Now there is potentially a problem with this definition. I mean, in fact, it isn't a problem, but potentially there is one there, and you're going to investigate this on your coursework. So I won't say any more about it. For now, we're just going to assume that this definition really does make sense and defines a binary operation on the set of integers modulo n, Zn, which you'll remember by definition is the set of all congruence classes modulo n. Then the Zn under plus is a group, and it's called the additive group modulo n. Its identity element is the class of 0, and the inverse of the class of A is equal to the class of minus A. So let's try some examples. Let's work in Z5 to begin with. So in Z5, what do we have? We have some things like 4 is a class, and also 2 is one of these classes. So if we do this sum, what do we get? By definition, that's the class of 6, okay, modulo 5, and the class of 6 modulo 5, that's the same as the class of 1 modulo 5, because 1 is congruent to 6 mod 5. 1 and 6 differ by a multiple of 5, so we know that their congruence classes are equal. So that is one example of an addition in the additive group modulo 5. Let's work out some more. In fact, let's work out the group table. So we're going to work out, here is our group table, and I'm going to label the elements as class of 0. I'm going to drop the subscripts because it makes it a little bit annoying to write down if you have to write a subscript 5 all the time. 1, 2, 3, 4, and those are the only different elements in Z5. Remember, in Z5, every congruence class is equal to one of the class of 0, class of 1, class of 2, class of 3, or class of 4. So those are the representatives we'll choose for these group elements. Okay, now first of all, class of 0 is the identity element in this group. So in this first row, what we will see is just the column labels copied out. And in the first column, the same thing will happen. So now let's look at this second line. We're going to look at the row which corresponds to adding ones. So class of 1 plus class of 1 is the class of 1 plus 1, class of 2. Next we'll get class of 1 plus 2, which is the class of 3, and the class of 1 plus 3, which is the class of 4. Then something interesting will happen. So it's perfectly correct to write down that this is the class of 1 plus 4, which is 5. That's true. But when we're doing a group table, we usually try to make sure that the elements in the table look like the labels for one of the rows or columns. So the class of 5 is, of course, equal to the class of 0, because 5 is congruent to 0 modulo 5. 0 and 5 differ by a multiple of 5. So what we could actually do here is put in the class of 0. Okay, let's keep going. Well, actually, one thing we can do already, this group is going to be an abelian group, a commutative group, because a plus b is always the same as b plus a. So we can actually copy what we did here and put it in the one column. 4 plus 1, class of 4 plus class of 1 is the same as class of 1 plus class of 4. So let's move in a layer and look at what happens next. The class of 2 plus the class of 2 is the class of 2 plus 2, it's the class of 4. Then the class of 2 plus 3 is the class of 5, and as we've seen, that's the class of 0. And next, well, we've done this calculation before, we get 1 here. So again, we have a 0, and again, we have a 1. We can copy them in because the group is abelian. So one more layer, 3 plus 3 is 6, and the class of 6 is the same as the class of 1 because 1 differs from 6 by a multiple of 5. 3 plus 4 is 7. And that differs from 2 by a multiple of 5. Okay, so then in our final layer, 4 plus 4 is 8, and 8 is congruent to 3 mod 5, so the class of 8 is equal to the class of 3. So there is our group table, our Cayley table, for the additive group modulo 5. And just one more note to make about this stuff, this is a cyclic group. It's a cyclic group generated by 1. And I think that's kind of easy to see when you just think about what it means to do the group operation in this group. Class of 1 plus class of 1 will be class of 2. Class of 1 plus class of 1 plus class of 1 will be the class of 3. Class of 1 plus class of 1 plus class of 1 plus class of 1 will be the class of 4. So we've made all of the non-identity group elements by adding together 1 some number of times. And the 0th power of 1 is defined to be the identity element, so the cyclic subgroup generated by 1 will be the whole group. So this is a cyclic group, and a generator is 1. There may be other generators as well. In fact, there are other generators in this case, but 1 is certainly a generator, and this is a cyclic group. So now let's think about the other type of group which we're going to meet today, which is the multiplicative groups modulo a prime. So we can define a binary operation of multiplication on Zn. In the obvious way, you can define the class of A times the class of B to be equal to the class of AB. So again, there are some issues about whether this really makes sense, and you're going to explore them on your coursework. That's one of the unassessed questions, is about why this definition makes proper sense. For now, we're just going to assume that it does make sense. And this time, this binary operation, it does have an identity element, and this time it will be the class of 1, for obvious reasons. If you multiply class of A by class of 1, you'll get the class of A times 1, which is the class of A again. So the class of 1 acts like an identity element, but Zn will not be a group under this binary operation. So the reason is a similar reason to the reason that the real numbers are not a group under multiplication, or the complex numbers are not a group under multiplication, or the set of n by n matrices is not a group under multiplication. The problem is some things don't have an inverse. In particular, the class of 0 will not have an inverse under the group operation, under the binary operation of multiplication. So that means the set Zn together with the binary operation which we've just defined is not a group. But things are even worse than this. When we talked about the real numbers or the complex numbers, we could just throw out the 0 element, and what we were left with was a group under multiplication. But that won't be the case for the integers modulo n. So as it says here, the integers modulo n with the class of 0 removed is still not always a group. And the reason for that, or one reason for that, is that multiplication doesn't even induce a binary operation on that set. So as you see here, if you take the integers modulo 6 and you throw out 0, so what you get is class of 1, class of 2, class of 3, class of 4, class of 5, multiplication is not a binary operation on that set. Because if you multiply together class of 2 and class of 3, well, you've got the class of 6. And the class of 6 is the class of 0, and the class of 0 isn't in that set. So you tried to combine two elements of that set using multiplication, and you got an element which wasn't in the set, so multiplication is not a binary operation on that set, and therefore that set with this particular operation is certainly not a group. So you can sort of see what the problem is there as well. I mean, the problem was that you can factor 6 into a product of two smaller things. 2 times 3 is equal to 6. So we might be able to save this if we were willing just to restrict to prime numbers. And in fact, it does work. So what you get when you do that is called the multiplicative group modulo p. And we're going to define it on this slide. If p is a prime number, then we define the multiplicative group modulo p to be as a set, the set consisting of the class of 1 mod p, the class of 2 mod p, up to the class of p minus 1 mod p. And this thing really is a group under multiplication. So I'm not going to prove that in this lecture. If you'd like to see a proof, you can look in the online notes, and that will explain why this thing is a group no matter which prime number p is. But what I will do is just look at a simple example. So let's look at the example, the first kind of, the first example where there's some space for something to happen is when p equals 5. So in this case, the multiplicative group modulo 5 will have size 4, and in general, the multiplicative group mod p has size p minus 1. So as a set, it consists of the class of 1, class of 2, class of 3, and the class of 4. Again, I'm going to drop the subscript 5 because it's a little bit tedious to write down. So again, let's write down the group table for the multiplicative group mod 5. So our rows and columns are labelled by 1, 2, 3, 4, and 1, 2, 3, 4, and 1 is the identity element. So in the first row and the first column, we just copy out the row and column labels. Okay, let's work out some more products. So 2 times 2 is the entry which goes here. Class of 2 times class of 2, or by definition of multiplication, that's the class of 2 times 2, which is the class of 4. So next we want the class of 2 times the class of 3. So that by definition is the class of 6. So it's perfectly okay to write the class of 6 here, but as usual, we actually want to write in elements which are row or column labels. So the class of 6 mod 5 is equal to the class of 1 mod 5, because 1 and 6 differ by a multiple of 5. So I can put a 1 there. Equally, 2 times 4 is equal to 8, and the class of 8 is the same as the class of 3, because 8 and 3 differ by a multiple of 5. So this is what my next row and my next column look like. And moving one step further in, we've got 3 times 3 here. The class of 3 times the class of 3 is the class of 9. And 9 is congruent to 4 mod 5. So this is 4. 3 times 4 is 12, which is 2. So we've got 2's. And finally at the bottom, 4 times 4 is 16, which is 1. Okay, so we can see what's going on here. And I will just observe that this is again a cyclic group. So Z5 cross is cyclic. For example, 2 is a generator. So if you look at 2 to the power, class of 2 to the power 0, that's the identity 1. Class of 2 to the power 1, that is class of 2. Class of 2 squared, that is 4, that's here in the table. Class of 2 cubed, that will be 2 times 4, which is 3. Okay, now class of 2 to the power 4 will be 2 times 3, which is 1. So 2 has got order 4. So we've already seen actually that all of the powers of 2 exhaust all of the elements of this group. And in fact it has. We've also seen that it has order 4 because we calculated all the powers, and the first power that got us back to the identity was 2 to the power 4. So it's a cyclic group, and the class of 2 is a generator. There may be other generators as well, but the class of 2 is certainly a generator. In fact, it's a general fact that the multiplicative group modulo p is always cyclic. It's not too easy to prove, but it is true. So there's something interesting about this multiplicative group, which is finding inverses. In a group, every element has an inverse. But in this group, how can we actually find the inverses? If you have a small prime number, then it's easy enough to do this by hand, just by brute force. You can just work out all the multiplications and see which one gets you back to the class of 1, which is the identity element. But in a large prime, with a large prime, you don't really want to do trial by error. So it would be nice if we had a method for finding inverses in the multiplicative group modulo a prime. On this slide, we're going to develop a theorem which will allow us to do this. What the theorem says is that if you have a prime number p and a number a between 0 and p, then there exist integers s and t such that a times s plus p times t is 1. And it's not completely obvious why that helps us, but I will show you in a second why that helps us find an inverse to the class of a modulo in the multiplicative group modulo p. In fact, the inverse of the class of A will turn out to be the class of S, and I'll show you why that is after I've explained a little bit about why this theorem is true. So I'm not going to do a complete proof of this theorem. What I'm going to do is show you how the calculation which proves the theorem works. So what we're going to do is we're going to notice that, first of all, we're going to divide p by a and get a quotient and a remainder. So when we divide p by a, what we're going to do is write p as a quotient, and I'm going to call this Q2 for slightly obscure reasons at the moment. Q2 times a plus a remainder R2, where this remainder is something which is between greater than or equal to 0 and less than a. So this is just doing integer division, dividing p by a and getting a quotient Q2 and a remainder R2, and that remainder's got to be a number which is greater than or equal to 0 and less than a. Right? When you divide by a, the remainder is always something non-negative, which is less than a. Okay, we're now going to keep going, and we're going to now divide a by R2. So a, we'll get a quotient, we'll call this Q3, and a remainder R3. And this time, this remainder R3, well, we divided a by R2, so the remainder must be less than R2. So R2 is bigger than R3, and R3 is greater than or equal to 0. Okay, we'll keep going. Now we're going to divide R2 by R3. When I do that, I get a new quotient, Q4, and I get a new remainder, R4, and this time we were dividing by R3, so R4 is going to be less than R3 and greater than or equal to 0. Now let's think what's happening with these sequence of remainders. So the remainders are all non-negative whole numbers, and R2 was bigger than R3, was bigger than R4. So this sequence is decreasing. It's getting smaller and smaller and smaller at every stage. So eventually it must hit 0. In fact, after at most a steps, it's got to hit 0, because that's the only place it can go. It's a strictly decreasing sequence, which eventually, so it must eventually hit 0. A strictly decreasing sequence of whole numbers, so it's got to eventually hit 0. So for the sake of illustrating the general argument, let's suppose it hits 0 at the next step. So when we divide R3 by R4, we get a remainder of 0. So that has to happen eventually, and let's say it happens now. Okay, let's think about what this sequence, what we can say about divisibility in this sequence. So what does this line tell us about divisibility? This line tells us that R4 divides R3. So I'm using this symbol to mean that R4 is a divisor of R3. R3 is a multiple of R4. Okay, now let's look at the next line up. So you've got R4 here, and you've got R3, which is also a multiple of R4. So both of the terms on the right-hand side are multiples of R4. So R2 itself is a multiple of R4, which means R4 divides R2. Okay, take this one step further up. R4 divides R3, and it divides R2. So every term on the right-hand side is a multiple of R4. So R4 also divides the left-hand side, which is A. Okay, one final step then. R4 divides R2, and it divides A, so it divides everything on the right-hand side of the equation. So it divides the left-hand side too, and R4 divides P. Okay, but P is a prime number, and R4 is less than A, so it must be a divisor of P, which is not P. So it must be that R4 is equal to 1. Because P is prime, R4 must be equal to 1. Okay, why is that use to us? Well, the thing is that this one here is this one here, because what we're going to do now is we're going to rearrange things using our knowledge about R4 being 1. So rearranging the third line of equations, let's just make ourselves a little bit of space here. Rearranging that third line of equations, what do I get? I get 1 is equal to R2 minus Q4 R3, which is equal to P minus Q2A, that's substituting for R2, minus Q4, and then we're going to substitute for R3, just moving up one step, so we get A minus Q3 R2. Okay, this looks like an awful expression. Don't worry, we're not going to care too much about the actual coefficients here. We're just going to make a point, which is that we can now keep going. So I've got P minus Q2A minus Q4 times A minus Q3 times P minus Q2A. Okay, close brackets, close brackets. All right, what have I got here? Everything that's happening here is either a multiple of A or a multiple of P. So every term involved in, when you expand this out, will be a multiple of A. So if you multiply out this horrible expression, I don't care what the actual coefficients are, but the point I want to make is this is something times A plus something, some awful mess, times P. And that is what the theorem claimed. We have represented 1 as a multiple of A plus a multiple of P. Now, the reason that this is useful is because what we can now say is, well, if you look at the class of A times the class of S, and I mean these classes modulo P, then that's the class of AS, okay, by definition of multiplication in the multiplicative group. But AS is equal to 1 minus PT, so AS differs from 1 by a multiple of P. AS is congruent to 1 mod P. Okay, if AS is congruent to 1 mod P, then the class of AS is the same as the class of 1, following our lemma that we proved earlier on. So, as I've written at the bottom here, the class of A times the class of S is equal to the class of 1, the identity element in the multiplicative group. Therefore, we found the inverse of the class of A. It is the class of S. So, if we want to find the inverse of a number A, or rather the class of A modulo a prime P in the multiplicative group, what we need to do is do this kind of chain of calculations and use it to write 1 as a multiple S times A plus a multiple T times P. And then the class of S will be the inverse of the class of A. So let's see that in action. we're going to find the inverse of 12 in the multiplicative group modulo 17. So what we need to do is just to do the calculations that we did in that sketch of a proof of a theorem. First of all, we write 17 as a multiple of 12 plus a remainder. So we divide 17 by 12, we get a quotient of 1 and a remainder of 5. Next, we move the thing we divided by over to the left, and we divide this by the old remainder. So we divide 12 by 5, and we get a quotient of 2 and a remainder of 2. So now we move our old remainder here, and we divide it by the next remainder, and we get 5 is equal to 2 times 2 plus 1. And at this point, well, the next step will give us a remainder of 0. So we can actually stop here because we've got the 1 that we're looking for, and we can now rearrange this. So the bottom equation, this one here, when we, oops, let's just get rid of that. The bottom equation says, when we rearrange it, 1 is equal to 5 minus 2 times 2. And now we can substitute for 5. 5 is 17 minus 12. So we're going to substitute this 5 for this 17 minus 12. And we're also going to substitute for one of those 2's. So the furthest up we can find a 2 is as 12 is equal to 2 times 5 plus 2. So we can substitute 12 minus 2 times 5 for one of those 2's. And then we can substitute again. I like the 17, I like the 12, the 2's multiplied in for something, I like the 12, I don't like the 2 times 5, but I can substitute 5 for 17 minus 12. And at this point, every term involves a 12 or a 17, so we can just multiply it out. And if you expand that, what you'll get is this last row here. So 5 times 17 minus 7 times 12. Now remember what the result said. The result said that the inverse of the class of 12 was the thing that you ended up multiplying 12 by in the expression for 17 as something times 12 plus something, in the expression for 1 as something times 12 plus something times 17. So the inverse that we want is the class of this. And don't forget that minus sign. The inverse is the class of minus 7, not the class of 7, the class of minus 7. So the inverse of 12, the inverse of the class of 12 modulo 17 is the class of minus 7 modulo 17. And if you'd like to represent that in our kind of standard form of integers, classes of integers between 1 and 16, then of course minus 7 differs from 17, minus 7 differs from 10 by a multiple of 17. So this is equal to the class of 10 modulo 17. So just to make that completely clear, 10, oops, wrong tool, 10 minus 7 is equal to a multiple of 17, so 10 is congruent to minus 7 mod 17, so the class of minus 7 is equal to the class of 10. Okay, so by this method we can find inverses in the multiplicative group modulo a prime. No matter what prime, no matter how large the prime, we can always do these calculations.